In this problem, we are asked to determine the isoelectric point, or pi, of the peptide, and we are given the amino acid sequence of the peptide written in one-letter code. Another convention that we need to recall is that when we have those one-letter or three-letter codes used for amino acid sequence of a peptide, the first one represents the N-terminal amino acid. So here is our N-terminal, or N-terminus, or N-terminal amino acid, and the very rightmost would be our C-terminus. Now, let's then recall that usually peptides acquire trans configuration, meaning that the side chains at all amino acid residues will alternate down or up the plane of the peptide bond. So I'm going to draw it right here in the middle of my page. I'll start with alpha amino group, then that's my alpha carbon here. Then I will show my first peptide bond, and then I continue in this direction. So I need to draw 1, 2, 3, 4, 5 amino acids. And right now I'm just drawing beta carbons. I haven't finished drawing side chains. Okay, so the first amino acid is cysteine, abbreviated as C. It has this beta carbon connected to tire group. Then we have H, stands for histidine. Then we have E, that stands for glutamic acid or glutamate. We have another E, another glutamate. And finally, we have R, which is arginine. Arginine has 3 methylene group, and then guanidino group after that. Now, let's list pKa's for each of the functional group. We'll start with alpha amino group. In peptides, it is around 8. Then we have cysteine side chain. It would be around 8.4. Histidine has a pKa around 6. Then for glutamic acid side chain, we will use a value around 4. Arginine side chain has a pKa around 12.5. And finally, alpha carboxyl group has a pKa of 3.5. Another thing to recall is that pi is a pH value allowing for maximal concentration of the neutral form. Neutral meaning that pH, charge, net charge is 0. If we analyze the pKa's that I listed and the charges overall, so I drew this structure around physiological conditions, around pH of 7. And so at this pH, we have 3 groups that are negatively charged, 1, 2, 3, but only 2 groups that are charged positively. In order to have a net charge of 0, we need to either protonate. Actually, we just need to protonate one group, right? And the only group that we can protonate without messing up other groups would be this histidine group. So we need to protonate it, so we pretty much need to put this proton here, and now it will have another positive charge. So now we have 3 positive charges, 3 negative charges. At what conditions, at what pH, I can actually protonate my histidine without, for example, protonating carboxyl group or deprotonating, let's say, thio group or alpha amino group. That will be at pH that is between the pKa for my histidine and the closest pKa for the carboxylic acid. So here I have 4. If I have my pH higher than 4, that allows for deprotonation of those groups. And still, if I don't exceed or don't approach too close to pH of 6, that will allow for the protonation of my histidine group. And so that would give me the pi of 5.